Okay, so we have this incline plane problem where there's a block of m mass and it's observed accelerating down from rest, down an incline, and the incline has friction, and it's at an angle theta from the horizontal. So how far is it going to travel in time t? So when we tackle this, keep in mind that we discussed that there are three components to Newton's second law, right? 3 dimensions. So these three one-dimensional forces in three one-dimensional forces in each direction, in each dimension, compose and they make up Newton's second law. So if we want to find, if we want to do a better job at solving these questions, I think we should look at each dimension individually, and then determine what's going on, right? So for f of z, so force in the z direction, so force in the z direction is equal to what? It's equal to the mass, which doesn't vary, times the acceleration, which does vary. So the acceleration is 0 simply because it does not move. There's no force being applied in the z direction, right? It doesn't tell us. It is not coming towards. It's going down. That's it. It's simply going down. So there's no force applied in the z direction. Now, that would mean that would simply mean that the velocity, if the acceleration is 0, then the velocity is constant. It's constant. And it's equal to 0. Why? Because if the acceleration is 0 and the velocity, if the acceleration is 0 and the velocity is constant, remember, it's the velocity is constant. If the velocity is constant, and we see here what it says in the question, from rest means from a place of not moving, right? And if it's constant, so what's the velocity if the object is not moving? It's obviously 0. The velocity is constant, therefore the velocity is equal to 0. Now, in the z direction, by the way, so velocity the z direction. Now, what about the acceleration in the z direction? Well, since velocity is equal to 0, then not the acceleration, sorry, the position. What about the position in the z direction? Since the velocity is equal to 0, and that means the acceleration, the position is constant too. And you might say, well, what do you mean constant position? Well, that just means it remains in terms of the position vector in the z direction, there is none. So this is 0. It's not moving towards the z direction. Now, since we discussed the z direction, now what about the y direction? Now, if we want to look at the y direction, we have to realize that the question tells us that it goes down. There's no part of this where the block is jumping up. So we have to write that f of y is equal to 0. But this is a little more complex than just simply being 0. And why is that? Well, you see down here that there's normal force, right? And that's part of the y component, but so is mg cos theta. But if it is equal to 0, then simply we can rewrite this as the normal force minus mg cos theta is just equal to 0. But remember that the friction, that the magnitude of the friction, I'll just write F for friction, is equal to what? It's equal to the coefficient of friction times the normal force, right? Here we figure out that the normal force is equal to mg cos theta, right over here, because if we rearrange this, n minus mg cos theta is equal to 0. Now add this to both sides. It cancels out here, so it becomes n is equal to mg cosine theta, right? That means our force of friction is the coefficient of friction times mg cosine theta. Okay? Now let's go on to the force in the x direction. Now the force in the x direction, if we see here, that you see the components of the weight. The components of the weight. This is a component of the weight. Wait, let me just fix this. This is a component of the weight. This is a component of the weight. And you see that the component of the weight actually is causing an effect in the x direction, right? It's causing an effect in the x direction, right over here. Right over here. To where it's causing the block to move this way. So now, you must ask yourself, if the block ends up if it accelerates downwards, but there is a force of friction, that must mean that the mg sine theta is greater than the force of friction, because if it wasn't, then it would never go down to the bottom. So we have to rewrite this as, I'll just write weight in the x direction. So we'll write actually I might switch I'll switch colors in a second. When we're doing the integration. So for this, we're gonna write W in the x direction. So W in the x direction minus the force of friction is equal to the total force in the x direction. Right? So that sounds good. Now we could write this out in a better way. So we could write this out as Wx is again mg sine theta minus, and remember the force of friction was the coefficient of friction times mg cosine theta is equal to what? Remember, force is just mass times acceleration, so the second derivative of the position vector of x, right? So now, of the x dimension. So now we could divide both sides by m, divide here by m, divide here by m. Now we're going to be left with cancel m out here, cancel m out here, m cancels here. We got g sine theta. Let me just move this down a bit. So we have now g sine theta minus the coefficient of friction. The coefficient of friction times gravity, or g, little g, acceleration due to gravity, times cosine theta is equal to the acceleration in the x dimension. Now that we got this, we can factor out the g. So factor out the g, and we're left with sine theta minus the coefficient of friction, not acceleration, times cosine theta. When I say acceleration, I mean this is the acceleration due to gravity. So now that we're left with this is our equation. So now that we have the acceleration, what we need is the position, right? We need the position because we need to see how far it travels as a function of time, right? That's what the question is asking, as you can see here. How far will it travel in time t? So it wants us to set up an equation as a function of time, as a position equation as a function of time. If we have acceleration, the simplest thing to do would be to integrate it. So I'm going to switch colors. Okay, so let's rewrite this. So the acceleration is equal to g sine theta minus the coefficient of friction cosine theta, and is equal to, that's it. Now we integrate this. Now integrating this, let's rewrite this. Remember what acceleration is? It's the derivative of velocity with respect to time. So let's rewrite this. Sine theta, and let me just rewrite everything we have so far. Okay, now that we got this, we'll multiply both sides by dt. Multiply both sides by dt, cancels out here. We're left with the derivative of velocity is equal to g sine theta minus, and then everything we have above, times dt. right? Now let's take the integral to get to velocity. And we're going to have to integrate twice because we're trying to get to position as a function of time. So now let's take it into, let's integrate this, right? So integrate the left side of dv and integrate let's integrate the right side. Now I'm gonna write from some velocity, the initial velocity, to some velocity at time t. That's our limit, and because this will be a function of time anyways, right? So over here too, so from 0 to t, and then we could do g sine theta. This is all a constant, remember, right? This is all a constant. This entire thing is a constant times dt. So what we're going to do is we're going to move this to the front, and then the integration of dt is just equal to t. It's just going to give us t, and we'll see that. I'll show that. Over here we're going to get, so dv, the integration of dv is just v. So then v sub t, and then we substitute these, we get, so velocity in time is roughly equal to minus the initial velocity, that's what we have on the left side, is equal to, now this is a function of time, or let's integrate this in with respect to the time limit that we have here. So this is a constant. Let's move it to the front. So g sine theta cosine theta, and then now we have the integral 0 to t of, there's a 1 here, right? And a constant times 1, sorry, the integral of a constant with respect to time is just time. So what we're really doing is just, this is what we're doing, right? Which is just going to be equal to, so if I set all this equal to a constant real quick, it'll be much easier for us. So if I just set, you know what, we'll just continue. So it's a little tedious, but it's okay. Cosine theta, and then evaluate times t, evaluated from 0 to t, which gives us, I'm not going to touch this for a second, so let me just rewrite, which gives us, this will give us g sine theta minus cosine theta, and then times, let's expand this, so t, you sub in t minus 0, which is just, this cancels out, so it's just t. So really what we get, and then we got to move this to the other side, so we'll be left with vt is equal to g sine theta minus everything we have here, coefficient of friction cosine theta, times, I'll just write t, plus the constant, the initial velocity. But if you remember that this starts at rest, our little mass is at rest in the beginning, so this is just equal to 0. We're not even going to have this. Now that we have this, it's time to integrate it the second time, so we can get this equation as a function of time. And I'm going to try to get another color. I'll just go, I don't know what color this is, but this looks nice, I think. Okay. Now, let's rewrite this. Let's rewrite Vt as dx over dt. You know what? I don't like this color. Hold on. Okay. So dx over dt is equal to g sine theta minus coefficient of friction times cosine theta t, and then times dt, right? All right, so far we got this. Now It cancels out here because we multiply by dt, and we're left with the integral of x naught to xt of d of x, which is equal to the integral of 0 to t of g sine theta minus the coefficient of friction cosine theta of and then times t dt. Let's do the left side first because it's just glaring. So how we're going to evaluate this is, first let's take the integral, which is, if there's a t here, remember that any constant is just if we have t, the integral of it will be t plus 1 or n plus 1 divided by n plus 1. I don't know why it's a bit tilted, sorry. So that's what we're going to get here. So t with n plus 1 divided by n plus 1, right? So basically what we're doing is squared divided by 2, right? So if it's n plus 1, there's an invisible 1 here, plus 1, so we're going to do 2, we're going to get 2, divided by the same n plus 1, so we're going to get 2 under it. So what we're going to be left with is this, essentially. G sine theta, I'm just going to divide it by 2. Instead of writing a half, we'll write a half at the end. Cosine theta times t squared, all divided by 2. And we have to evaluate this still from 0 to t. And we substitute t in, that stays fine. We substitute 0 into this entire thing turns into 0. So what we're really just left with is this what we have going on right here. On this side though, we got, so the integral of d of x, that's just x. So we sub this in, we have x of t minus x sub o. And now we'll just rewrite the last part of this. So x of t as a function of time is equal to 1/2 g sine theta minus the coefficient of friction cosine theta, and then t squared. Not sure why I wrote these brackets. I mean, it's no problem, but it's whatever. And then plus and the initial position, which if you remember it's at rest, and that's our origin, which it is. Rest is our origin, then this is equal to 0. So what are really our final answer, and I'll write it in a different color just for the good old pink. So final answer, so final answer is equal to x of t is equal to 1/2 g t squared sine theta minus coefficient of friction cosine theta. And yeah, that's our final answer. And what this gives us is the position as a function of time. We could find out how far did something travel in time t, because it is dependent on time t. So this is a function of t, and that's exactly what we just found.